Ladies and gentlemen, this is a short introduction to the background of stereographic projection, how it in principle works and what we can do with this. Stereonet projection is useful to reduce the three dimensions of structural data as we see them in nature, in the field, into two dimensions so that we can show them in a diagram format, which is important because we are communicating essentially in two dimensions, not in three dimensions. We communicate data on computer screens or in printed form, not in three dimensions, and that is what these diagrams are helpful for. We can show our database on these stereonets. That means the linear and planar structures that we record in the field during our structural mapping, and we can later analyze on the stereonet these data, particularly with respect to their geometrical and angular relationships. That means the angle between planes, the angles between lineations or lineations and planes, and so on. We also can use them for higher level stuff, paleo stress field analysis. We can analyze fold geometries, hinge lines and actual surfaces of folds, cluster analysis, which is important for statistical analysis, which allows us, which is possible in contour diagrams, and we can do data rotations. If geological processes have rotated our structures in the field, we can reorient them into their original position. At second year level, we are focusing essentially on the first 2 points, portraying our data, showing our data in the Stereonet, and analyze some very basic angular relationships. So let's go back to material that you have already heard about in your first year courses. Basic things like strike and dip directions and dip angles. You might again recognize this diagram from your undergraduate textbook. It shows here a field situation with an outcrop of a layered sequence shown here as light brown and dark brown, possibly sedimentary layers that are cropping out along a ridge in a lake. And this is shown here on the geological map. So here we see the plan view with our north direction with a scale, and we see where the geologists have mapped out the distribution of these different layers on that ridge in that lake. Obviously they didn't dive down to the bottom of the lake. If they had done so, they probably would have found these young sediments that we see here shown in our block diagram. But let's stick with the important tilted layered sequence that we see here, and that layered sequence has a certain orientation that we see here in 3 dimensions with respect to the compass rose. We see here the north direction, and we can see here this ridge runs roughly to the northeast, or from the northeast to the southwest, and that is also shown here in our plan view on the geological map, with the lower light brown layer with a layer in the middle, the dark brown one, and then on top this other light brown layer, as we see them here, inclined, tilted at a certain angle in the field, the lower light brown, the central dark brown, and the top light brown layer that we see here. We see here an image of the compass rose, which is nothing else but a finer segmentation of the general compass directions, north, south, east, west, and everything in between, subdivided into 360-degree segments that run from north to the east, to the south, to the west, and back to the north. If we look at such an inclined layer, we always will be able to draw a horizontal line onto such a surface, and this direction is here highlighted in that blue line. That is the strike line of that surface. It's always horizontal, and that's why it's convenient here to draw it parallel to the sea level, which is obviously also a horizontal surface. So here we are the level of that lake, the water level meets this inclined plane. It will form a horizontal intersection line parallel to the strike line. And we see here that strike line has two ends, one over here in the northeast and another one in the southwest. And on geological maps, you probably will have seen very often these strike and dip symbols, these symbols that portray, that symbolize the orientation of the planes. And as we see here the blue strike line, we would see here the long line of that strike dip symbol. This is the long. The long line is always parallel to the strike of the surface. And then we would have here that small dip line. We come back to that later. So if we see here that strike line in the field, we can measure its orientation with a compass. And we see here in this case the strike line is at 40 degrees with respect to north. That means this end of the strike line points almost exactly to the northeast, and the other end of the strike line would point to the southwest. We see here that is 220 degrees. That is what you can measure with the compass, and here on the compass rolls we see that angular relationship between the 40 degrees in the northeast and the 220 degrees right in the opposite direction. They are connected by 180 degrees. If we add 180 degrees to 40 degrees, we will end up with 220, and that is always the angular relationship between the two ends of the strike line. One end of the horizontal line, of any horizontal line, points in the opposite direction of the other end. 180 degrees are in between. Then we have here the dip line. The dip line is a line on the surface that is the steepest possible line. So on that layer, a bedding plane perhaps, we would have one direction on which water would flow down, or if you put a marble onto a surface, it will roll down in the steepest possible way, and that is the dip line of a planar surface. And we see that here in our map symbol, the dip line is always the short line. It points in the direction in which the layers are steepest in their inclination. That is called the dip line. Now, very closely related to the strike line and the dip line is the dip direction. We see here the dip line. We can also draw it here onto our strike line. This orientation is just in the same direction as the dip direction. The dip direction is an azimuth. As the strike line, it can be expressed as a compass direction. That means as a direction between 0 and 360 degrees. And we see here the dip direction and the strike direction and the dip line are closely geometrically related to each other. The dip direction is always related by 90 degrees with the ends of the strike line. We see that here 40 plus 90 equals 130 degrees, and 220 minus 90 also produces this value of 130 degrees. But you need to pay attention. You cannot use that relationship uncritically, because if you add or subtract to the wrong ends of the strike lines, you might end up with the wrong dip direction. 40 degrees plus 90 is 130 degrees, but if you calculate 220 plus 90, you end up at 310 degrees, and that is not the dip direction of our plane. These planes here are clearly inclined towards the southeast, towards 130 degrees, not to the northwest or 310 degrees. So make sure that when you think about the relationship between strike lines and dip directions, you are not uncritically just randomly choose one of these strike lines and add or subtract 90 degrees. You need to be aware of the three-dimensional direction, because 90 degrees adding or subtracting might easily give us the opposite direction of the true dip direction of the plane. We will come back to that later when we talk about the right-hand rule, but for now, be aware there is a pitfall. So otherwise, this is fairly straightforward. The strike direction and the dip direction are both azimuth directions. They all are related to the compass rose, and they are horizontal directions. So you stand in the field, you point horizontally in some direction, you will get the azimuth. And if you are aware of or if you have measured the strike and dip direction of a geological surface, that is what you would record in your field notebook. So then we have the dip angle, which is different from the dip direction, and you need to be aware of that. The dip angle describes how steep this layer is oriented, and that would be the angle between the dip line and the dip direction. This angle can be measured also with the compass and the field, and here in this example this is an angle of 30 degrees, and on geological maps the dip angle is usually recorded as a number. We see here the strike line, we see here the dip line, which is on a map identical to the dip direction, and we see here the 30, which is the number of the dip angle. These are shallowly to moderately inclined layers, dipping at 30 degrees. If they were vertical, they would have a dip angle of 90 degrees. If they were very shallowly inclined, they might have a dip angle only of a few degrees, 5 degrees or 10 degrees. And therefore, from this number you can read how steep is that orientation of that surface. Okay, so ensure that you are aware of the geometrical meaning and the geometrical relationship between dip line, dip direction, and the strike line. Only the strike line has two ends and two directions, which are on the compass rose opposite to each other. The dip direction has only one azimuth, which is important because no feature of this surface is actually oriented in the opposite direction. So the dip direction has only one end, the strike has two. Here we see an example from the field. A fault surface developed in gneisses in the Namako belt, and that is what you probably would observe. You see here the fault surface itself, and you see these striations. These are slicken lines. There are also slicken side steps that you can see here, and you might remember how these features are interpreted from the first year course. And with a compass we can measure a horizontal line, the strike line on that surface. This would be this direction here, and here this would be the dip line of the fault plane. So here this is our strike, two ends of a strike line, this is the dip line, and what we have recorded here is the dip direction, 177 degrees. That means it's a almost south dipping plane. 180 degrees would be a south dipping plane, and the strike would be roughly east-west. It is not a very steeply inclined plane, 33 degrees. That is our dip angle. So that is one way of recording the orientation of this fault plane. Similarly, we can measure the trend and the plunge of these striations. Also that can be done with a geological compass, and these striations have a trend of 107 degrees. That means they are trending into a southeastern direction. 90 degrees would be east, so that's east-southeast, 107 degrees, and they are very shallow, 12 degrees inclination from the horizontal, so a shallow plunge for these striations that give us the movement direction of the fault at the time when it was tectonically active. So trend and plunge of lineations and the strike and dip directions and dip angles of planes. These are the geometrical parameters that allow us to record the orientation, the three-dimensional attitude of planar and linear structures. Now this is how the Stereonet actually looks like. It looks a little bit like a planetary map with longitudes and latitudes, and there are some similarities, but it's not quite the same. We see here a segmentation of the Stereonet in 2 degrees intervals, again from 360 at the top to 90 in the east, 180 south at the bottom, and 270 in the west. And we see 2 sets of circles. Here 2 are shown and highlighted. Great circles run always from the north to the south, and there are plenty of them. Not only this red one you see here, they go in all kinds of directions, and they are usually shown in 2 degrees intervals. That is what we call the great circles. The small circles are running here from east to west, and they are shorter, closer to the north and south of the Stereonet, and they are longer here in the center. There's only one straight line, and that is the small circle that connects the east and the west. Also, the only straight great circle is the one that goes from the primary directions, here from the north to the south. All other lines are curving, the small circles and the great circles. So what does that mean? What does it actually tell us? This is the so-called lumbar equal area projection, also called the Schmidt-net, one of the most commonly used projection types in structural geology. How does it make sense? Obviously, it has something to do with the compass rose, since we are using the same 360 degrees segmentation. And what it actually means is shown here by this model. Normally we would do that in the classroom. Here in the online version it might be a little bit more difficult to grasp. What we are seeing here is a bowl shape of a lower hemisphere. You can think about a globe. You have all seen globes of the Earth. Here we are looking at the lower part of such a globe as if that globe was cut through along the equator. And it's this equatorial plane on which we need to think of as the Stereonet. Now here we have this plexiglass surface that we can rotate in our model, and here it is inclined a little bit, and you see here that planar structure, this planar surface is now tilted here to the east. That might pretty much be a plane that is dipping maybe in the direction of about 100 degrees. We will see that in a moment. We see also here that this plane that we have has here a rod through it, which is the normal direction. It's just straight down at 90 degrees to the surface of the plane. We have inserted here a rod. We will get to know that as the pole to the plane. So the Stereonet is a projection. It's a two-dimensional projection of structures within this three-dimensional lower hemisphere. So the orange surface here would be the equatorial plane that we see here, and we can actually put into that system any kind of orientation of planar and linear structures, because we obviously can play with our little model here with this planar surface and position it in any direction that we like. So when we come from the three-dimensional attitude, the three dimensions of the lower hemisphere, into the two-dimensional space of the Stereonet, we are reducing one dimension. We come from 3D to 2D, and that is exactly what we want to achieve in this projection. So let's have a look at this surface here, this purple surface. It is now oriented in a specific orientation, as there might be a stratigraphic layer in the field or fold plane or any other plane in the geological world. And we see here this planar surface has an intersection line with the lower hemisphere, with this bowl-shaped body of the lower hemisphere. And we see here that highlighted as a circular, as a curving intersection plane that we see here. We see it here ending because it's hidden by the rim, but actually this intersection plane ends up here at this point. And we can see that this point here is right opposite of that point where the intersection line starts. You might guess that this indicates the strike of this plane. Then we see here the rod of the pole to the plane. This is here the direction of the pole to the plane. This is now a not three-dimensional plane. This is a two-dimensional line, and this two-dimensional line intersects in a one-dimensional point with the lower hemisphere. That would be down here at the bottom of the lower hemisphere. That is where this line intersects. And you will have seen here a three-dimensional plane intersects with the lower hemisphere in a two-dimensional line, and a two-dimensional pole to the plane, so a linear fabric element, intersects in a one-dimensional point. So in both cases we reduce one dimension, and again that is what the projection means to achieve. Coming from 3 to 2 dimensions, or for linear fabric elements which are two-dimensional, come to a one-dimensional point. Let's stick with lineations for a moment. You remember our example here from the Dinamarca belt. We see here that fold surface. On the fold surface we see the slicken lines. These are linear fabric elements. They are developed on a planar surface, but each for itself is a line, and such a linear feature can be shown on such a fold surface. Let's assume the purple here is the fold surface. These are the slicken lines, and these slicken lines can be expressed in an azimuth, the trend. And we start from the center of that plane, and we just look along the lineation in the horizontal direction. That gives us the trend. And we have here, determined by the steepness of the plane itself, the plunge, which gives us the steepness of the lineation. So that would be the plunge, here in yellow. That would be the trend. And the trend is expressed between 0 and 360 degrees as an azimuth. The plunge ranges from horizontal, that would be a horizontal lineation, to a vertical lineation, between somewhere 90 degrees and 0 degrees. In our example, we have seen that this here is a shallowly plunging lineation of 12 degrees. So here we see again a kind of attempt of a three-dimensional portrayal of the lower hemisphere. You see that here, and the projection works as follows. Imagine that you look from above onto the lower hemisphere. From an observation point above, you look at the intersection point of such a lineation. Here we see a lineation. We imagine it starts in the center of the Stereonet and extends further down until it hits the lower hemisphere. Seen from our observation point, we can imagine there is a line from our eye, from our observation point, to the intersection point of the lower hemisphere. somewhere on that way between observation point and intersection point, we are going through the equatorial plane of our lower hemisphere. That is our Stereonet. And at this point, that is the point where our lineation will plot on the Stereonet. So again, your observation point is up here. The intersection of your lineation with the lower hemisphere, with that bowl, is here. And your Stereonet is here on the way from observation to intersection point, and where the observation line from observation point to intersection point hits the Stereonet, that is where the lineation will plot. In this example here we see north, east, south, west. We see a lineation that trends to the southwest, more specifically at 246 degrees, which is between 180 and 270 degrees. And this lineation is inclined at 19 degrees plunge, and that brings it to this red dot. This red point is also shown over here. And when you look here from the center of the Stereonet and you draw a line from the center of the Stereonet through this point, you will come here to 246 degrees. That is the trend of this lineation. Now this lineation is not particularly steep. It's only inclined at 19 degrees, a fairly shallow plunge. All shallow plunging lineations produce points on the Stereonet that plot fairly close to the outside perimeter of the Stereonet. And depending on the trend, whether this is a north, an east, a south, or like in this case here, a southwestern trend, it will plot in different positions of the Stereonet. So let's here have a look. This is our 246/19 lineation, a shallow southwest plunging lineation. Here's now a different lineation. This one is steeply oriented. It has a plunge of 80 degrees and it trends to the southeast, into the southeastern quadrant at least. And from our observation point, we would look at the intersection point of this lineation and we will find this is fairly steep down. It's almost in the center of our lower hemisphere. And if we draw a line from the observation point to the intersection point, we hit the Stereonet, the equatorial plane, fairly close to the center. This point represents this intersection point. So we can learn from that steeply oriented lineations plot closer to the center of the Stereonet than lineations that are more shallowly inclined. Lineations that would have a plunge of 45 degrees would plot halfway between center and perimeter. Now let's have a look at planes. Again, here in this graphics, we see here the Stereonet, the equatorial plane. We see here the lower hemisphere. And we see here our observation point, and this diagram also shows the upper hemisphere. We actually don't really need that upper hemisphere. All we need is this observation point. And now imagine there is a plane oriented here with a certain strike. In this case here, that seems to be a north-south strike. And this plane is inclined, is dipping to the east, here to our right-hand side. And this plane will intersect with the lower hemisphere along this curving line. This curving line describes the intersection of the plane with the lower hemisphere. And when we observe this intersection line from our observation point. We can look here in all sorts of directions to this part of the intersection line, or this, or that, or that, or that, or that, or that. And if we connect the dots that we are getting on the Stereonet, we produce such a curving line, which, as you might have guessed, is a great circle. This great circle ends at one end of the strike line of the plane and at the other end of the strike line of the plane. What is called here projection plane is simply the Stereonet. And these little dots here are randomly chosen positions along the great circle that is projecting the intersection line of the plane with the lower hemisphere. Let's try to get that somehow together with our three-dimensional model that we see here on the right hand side. Again, we have here our lower hemisphere. We have here the plane intersecting, and this plane is here extrapolated into this rectangle to symbolize that this is part of a larger geological surface. So this geological surface is oriented in such a way that it forms this kind of curving intersection line, which describes the strike. And in this example here, north, east, south, west, this strike line is shifted by 20 degrees with respect to north. That means one end of the strike line is 20 degrees. Accordingly, the other end of the strike line is 200 degrees. Now clearly this surface here is inclined towards the east or east-southeast and not here to the west-northwest. Because with the same strike here, with the same strike line, around that strike line you just could tilt this plane so that it dips actually into the northwestern, not into the southeastern directions, without changing the strike. If you rotate that surface around this strike line, you are not changing the strike, but you might change dip angle and eventually, if you tilt further, the dip direction, and then this plane could dip to the left-hand side, not to the right-hand side of our model. This would change the dip direction, not the strike. That is why it is important to be always aware of the dip direction. And that is what we see here. We see here the dip direction of that plane is 20 degrees plus 90 is 110. The dip direction is not opposite. It's not 200 plus 90. Then this surface would be inclined in the opposite direction towards 290 degrees. So now obviously every surface has a strike and a dip line, unless it is a horizontal surface, then it doesn't. But every inclined surface has such a strike line that we see here, 20 to 200, and it has a dip line which is simply the steepest possible line on that surface. That is the line along which water would flow down or a marble would roll down if you put it into the center, onto the center of that plane here. So a symbol in our three-dimensional graphics, we see the dip line here, and the dip line here is right in the middle, halfway along this intersection line from the one strike line to the other strike line. Now we see it here on the model and here in the diagram. And if we connect the dip direction, the dip azimuth, 110 degrees, with that dip line, we can measure the angle in between, and that would be the dip angle of the surface. That tells us how steep that surface is inclined. And that would mean this here is moderately inclined, not quite halfway between a horizontal surface, which would have a dip angle of 0 degrees, and a vertical plane, that would have a dip angle of 90 degrees. How do we write down these data? There are two important notation methods. One of them is the right-hand rule strike and the dip angle. RHR stands for right-hand rule, and in a moment we will see what exactly that means. That refers to one end of the strike line. In this case, it's this one. And we would write that down as a right-hand rule strike and dip angle of 0.20 for the 20 degrees, slash 40 for the 40 degrees dip angle. This is the notation using the right-hand rule strike, one of the two, and the steepness, the dip angle of the surface. In my view, a better way to write down and to record the orientation of planes would be the dip direction and the dip angle. In this example here, 110/40. That is probably the more commonly used way, but both right-hand rule strike and dip angle and dip direction and dip angle you will find in the literature and textbooks. There are a few other methods that you also might come across, but these two are the most important ones. Let's have a look at the Stereonet, and we see here a variety of great circles for planes that all strike north to the south. And a plane that is vertical will produce a great circle that is a straight line from the north to the south. This plane will have a dip angle of 90 degrees. A plane that is fairly steeply oriented, say dipping at 70 degrees to the east, will produce a great circle that follows this slightly curving line. But it will run through the Stereonet fairly close to the center. Here's the center of the Stereonet. Steeply inclined lines produce great circles close to the center. You remember that's the same principle like with the lineations. Steep lineations form points. They plot close to the center of the Stereonet. Steeply inclined planes produce great circles that also run through a position close to the center. If the plane is a little bit shallower, but still dips to the east, 50 degrees, your great circle becomes more curving. And we can follow that here at 30 degrees or to 10 degrees. And a plane that is almost horizontal, maybe dipping only at 2 degrees, will run through the Stereonet almost at the perimeter. And a horizontal plane will intersect with the lower hemisphere right at the rim. And it will run around the whole Stereonet. Now if we use planes that have exactly the same strike from north to south, but don't dip to the east, but to the west, they still maintain their north-south strike. But the great circles will run through the western side of the Stereonet, and depending on dip angle, closer to the center or closer to the perimeter. So here we have a variety of north-south striking planes that either dip to the east or they dip to the west at various dip angles. Not all surfaces strike north-south. You might have here a selection of planes that strike from roughly 75 degrees here to values of 255 degrees, 180 degrees away. So these are the ends of the strike lines, one over here, one over here, and the great circles connect these two ends of the strike lines at various dip angles, shallow towards the rim or steeper closer to the center. And they are bulging all in the dip direction. the dip direction of all of these planes here is 75 plus 90 degrees, 165 degrees. Accordingly, you have 255 minus 90 degrees ends up at the same position. So dip direction would be determinable here from the strike, either plus or minus 90 degrees, but be careful that you are not adding 90 to the wrong end of the strike line, because that would give you then a dip direction of 345 degrees up here. And this would be then a plane dipping to the north-northwest at shallow angles, steeper angles, or very steep angles. So again, be aware, strike plus 90 or strike minus 90 gives you the dip direction, and you need to be aware which is the actual true dip direction of the plane, because otherwise if you add or subtract 90 from the wrong end of the strike line, you end up with the wrong dip direction. Let's just recap on the notation of planar compass readings. There are a number of different methods. The two important ones are highlighted here. It's the right-hand rule and the notation as dip direction, not strike, which is called the Clar notation. These are the two important ones. There are others who simply choose either of the strike lines and produce a value between 0 and 360 degrees. If you do that, you have to tell the people what is the dip direction of the plane. So a plane that has a strike east-west, 90 degrees or 270 degrees, you can choose either of them, but then you have to tell the people whether this plane is dipping to the north or to the south. Then there are some people who say, well, since we have always two ends of the strike line, one end of the strike line will fall always between 0 and 180 degrees. And that is the one we are using. So we always use the smaller of the two strike lines. But again, then you have to specify the dip direction. Because if you say, well, our east-west striking plane that has a 90 and a 270 strike, we are using the 90 of the two because it's a smaller one, but you still could have a north or a south dipping plane. The right-hand rule we will look at in a minute. The right-hand rule is always the dip direction minus 90 degrees, as we will see. And the Clar notation is the dip direction, and as we see the dip direction, as we have seen, the dip direction has only one end that is unequivocal, and it's given a number from 0 to 360 degrees depending on in which direction this plane is dipping. This is my preferred notation method, the so-called Clar notation, dip direction, not strike, because you are not getting confused with the two possibilities of a dip direction related to a specific strike direction. Then unfortunately there are exotic things like the quadrant notation. This is, in my view, an outdated and complicated method. Unfortunately, the textbook Davis and Reynolds, which is otherwise not a bad textbook, uses this quadrant notation, but I'm not going to explain it here because it's just confusing. Let's focus on the two important ones, the right-hand rule and the Clar notation. Both have in common that their dip angle, that means how steep is the plane, is always recorded as a value between 0, horizontal planes, and 90 degrees, vertical planes. And our notation is always the first value. That should be either the right-hand rule strike or the dip direction, using 3 digits, because we can run up to 360, which is a 3-digit number, and a second value after a slash, which gives the dip angle in 2 digits, because the maximum value here is 90 degrees, a 2-digit number. On this diagram here we see the strikes of an inclined sequence of strata. We see again the two ends of the strike line. In this example here, that is 270 degrees or 90 degrees, so we are looking here at the east or the west. And this plane here dips to the north. We see that here it comes towards us, and if west is on our right hand side and east is on our left hand side, a plane that dips towards us is obviously dipping to the north. The dip direction would be straight north, 360 degrees or 0 degrees if you want. And here in this example, if we take a notation of using this end of the strike line, it would be 270/50, but we have to specify that it's a north dipping plane, because it also could be a south dipping plane using the same east-west strike. Accordingly here, if we write down this plane as 90 degree strike with a 50 degrees dip angle, we again have to say this is a north dipping plane. This is how we communicate that if we have unspecific ends of the strike lines that we want to use. And that is another recording talking about the same plane, a north dipping plane with a 90 degree strike and a 50 degrees dip angle. Here's the right-hand rule. The right-hand rule ends this confusion of the two possible strike lines. With the right-hand rule, you always use that end of the strike line in which your thumb would point if you put your right hand down onto such a plane with your fingers parallel to the dip line. So here this hand is showing the dip line with your fingers, and you stretch out your right thumb. This would be the right hand rule strike. And in this example here, it's 270 degrees. A right hand rule strike of 270 implies that the dip direction of that plane is to the north, because your right thumb would always point in a direction that is 90 degrees smaller than the dip direction. So the dip direction here is 360 minus 90 degrees gives you 250. Again, in my view, more convenient, less confusing is taking the dip direction straight away. The dip direction is 360. In our example here, 360/50. When you write a document, a report or a thesis or anything like that, you have to tell the reader up front what kind of notation you use. Are you using right hand rule notation? Then the reader would know this number here refers to the right hand strike and this here to the dip angle. If you tell your readership you are using Clar values, then the first value here will be the dip direction, followed by the dip angle. It is a bit unfortunate that there is no uniform agreement on the way the notation of structural data happens. Companies might have the one or the other rule that they prefer and that they have agreed on using, and that is the reason why you have to know at least about the Clar and the right hand rule methods, because you might join a company that might use the one or the other. Linear structures always refer to the trend, that is the direction in which the lineation points between 0 and 360 degrees, and the plunge, which is either horizontal 0 degrees or vertical 90 degrees or anything in between. And the notations for all methods except the unfortunate quadrant method is that the first value again gives the trend in 3 digits, is this north or south? If it's north, it's a 360, followed by a slash, and the plunge in 2 digits. Is it shallow, 10 degrees? Is it moderately, 45 degrees? Or is it a steeply plunging lineation, 80, 85 degrees perhaps? So these are the important ones. Rake and pitch is the last thing I want to mention. This is again something that is not uniformly used. These terms sometimes have different meanings. Most people agree that rake and pitch is the same thing, and the same is the same thing. And in contrast to the plunge, which is the angle between the trend and a lineation itself, the rake is measured always on a planar surface. So you have here the roof of this little den for our piggies. The crest would be the strike line of this surface, and here is the rake and the pitch. It's usually synonymous, the same thing. These are lineations on that surface, and the angle between the strike line and the pitch or the rake, that is an angle that we can measure, which ranges between 0 and 90 degrees. So in this example here, the rake or the pitch of these two lineations would be 65 degrees measured from the southeastern end of the strike line. And that is important. You have to record that, because 65 degrees from the northwestern end of the strike line would be lineations that run in this direction, and that clearly is a different orientation from the lineations that we have in our example. For your smartphones, there are a number of useful apps for the Stereonet. 2 of them I have tried. They are both reasonably useful. One of them is the Lumber software, which works only on iPhones or iPads and costs a bit of money. And there's Pocket Transit, which works either with the iWorld or with Android phones. You can try them out, upload them, download them, and play with them. And I believe there are a number of other apps now on the market that are doing stereographic measurements. You even can use your own phone like a geological compass. It's not quite as convenient as easy as a analog compass, but it works. So I encourage you, use your electronic devices to learn a bit more about Stereonets. That would be the first part. In the next part, we are introducing Stereonet software and how to feed this software with data readings obtained in the field, and how to analyze these data. That will be a different video. Thank you very much.